Introduction to BGP Traffic Engineering. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're diving deep into BGP traffic engineering, a critical skill for network engineers managing multi-home networks or working with multiple ISP connections. Traffic engineering with BGP is all about controlling how traffic flows into and out of your autonomous system, and it's essential for optimizing performance, managing costs, and ensuring reliability. In this comprehensive presentation, I will walk you through the fundamental concepts, practical techniques, and real-world scenarios that you will encounter when implementing BGP traffic engineering. Whether you are preparing for certifications, working on a network design, or troubleshooting existing BGP configurations, this presentation will provide you with the knowledge and tools you need. We'll start with the basics of BGP path selection, and then progressively move into more advanced topics like community-based routing, traffic manipulation techniques, and best practices for production environments. I'll share examples from real deployments I've worked on, including multi-cloud architectures and enterprise WAN designs. Understanding BGP path selection. Before we can effectively engineer traffic with BGP, we need to understand how BGP makes routing decisions. The BGP best path selection algorithm is deterministic and follows a specific order of criteria. This is fundamental because all our traffic engineering techniques work by manipulating these selection criteria. Let me walk you through each step of the BGP path selection process. First, BGP checks if the next hop is reachable. If it is not, the route is immediately discarded. Then, it looks at administrative weight, which is locally significant to the route. After that, comes local preference, which is significant within your autonomous system. The algorithm continues through AS path length, origin type, MED, multi-exit discriminator, and several other criteria. Understanding this order is crucial because it tells us which attributes we need to manipulate to achieve our traffic engineering goals. For example, if you're trying to influence inbound traffic from your ISP, changing your local preference won't help because your ISP never sees that attribute. Instead, you'd need to use AS path prepending or MED values. In my experience working with service providers and enterprises, I've seen many engineers struggle with BGP traffic engineering because they don't fully grasp this selection process. They might try to use MED to override AS path length, not realizing that AS path is evaluated before MED in the decision process. Controlling outbound traffic. Now, let's focus on controlling outbound traffic. This is the traffic leaving your autonomous system. This is typically easier to control than inbound traffic because you have direct control over your own routing decisions. The primary tools we use for outbound traffic control are weight and local preference. Weight is a Cisco proprietary attribute that is locally significant to a single router. It is not advertised to any BGP peers, not even to IBGP neighbors within your own AS. The default weight is 0 for learned routes and for locally originated routes. When you want to influence traffic on a single router without affecting the rest of your network, weight is your go-to tool. Local preference, on the other hand, is shared throughout your autonomous system via internal BGP. The default value is 100, and higher values are preferred. This makes local preference perfect for implementing AS-wide routing policies. For example, if you have multiple exit points to the internet and want all traffic to prefer ISP1 over ISP2, you would set a higher local preference on routes learned from ISP1. In the code example on this slide, I am showing you how to implement both weight and local preference using route maps. Notice how we match specific prefixes or AS paths and then set the desired attribute. This granular control allows you to implement complex routing policies based on your business requirements. Controlling inbound traffic. Controlling inbound traffic is more challenging. This is because you are trying to influence routing decisions made by other autonomous systems. You cannot directly control how others route to you, but you can influence their decisions using several techniques. The most common methods are AS path prepending, MED, multi-exit discriminator, and BGP communities. AS path prepending works by artificially lengthening your AS path by adding your own AS number multiple times. Since BGP prefers shorter AS paths, this makes a route less attractive. For example, if you have two ISP connections and want most traffic to come in through ISP1, you would prepend your AS number several times when advertising to ISP2. MED, also known as metric, is used to influence routing decisions when you have multiple connections to the same AS. Unlike AS path prepending, MED is only compared between routes from the same AS. The lower MED value is preferred. This makes MED perfect for scenarios where you have multiple connections to the same ISP and want to indicate which link should be preferred for specific prefixes. One important thing to note with MED is that many ISPs reset MED values at their borders or ignore them entirely. Always verify with your ISP whether they honor MED values before relying on this technique. In my experience, AS path prepending tends to be more reliable for influencing inbound traffic, though it's a coarser tool. BGP Communities Overview. BGP communities are one of the most powerful and flexible tools for traffic engineering. A community is essentially a tag that you can attach to routes, and these tags can signal specific actions to upstream providers or peers. Communities are transitive optional attributes, meaning they can be passed between autonomous systems if configured to do so. There are three types of communities: standard communities, 32-bit values; extended communities, 64-bit values; and large communities, 96-bit values. Standard communities are the most common and are typically represented in the format ASN:value, like 65001:100. This format makes it easy to identify which AS defined the community and what it means. Well-known communities have special meanings defined in the BGP RFCs. NO export prevents a route from being advertised outside the AS. NO advertise prevents a route from being advertised to any peer. NO export subconfed prevents advertisement outside a confederation. These well-known communities are particularly useful for controlling route propagation. Many service providers publish their community values and what actions they trigger. For example, a provider might use 65001:70 to set local preference to 70 within their network, or 65001:666 to trigger black hole routing. Always check your provider's documentation or routing registry entries to understand what communities they support. Implementing BGP communities. Let me show you how to implement BGP communities in practice. The process involves three main steps: defining the communities you want to use, applying them to routes, and configuring actions based on those communities. This is where route maps become incredibly powerful. When setting communities, you have several options. You can use set community to replace all existing communities, or set community additive to add communities while preserving existing ones. The additive keyword is crucial when you want to stack multiple communities on a route as it passes through your network. In the configuration example, I am showing a common pattern where we tag routes based on where they were learned and what type of routes they are. For instance, customer routes might get tagged with 65001:100, peer routes with 65001:200, and transit routes with 65001:300. These tags then allow us to implement consistent policies throughout our network. One best practice I always recommend is to use a consistent community numbering scheme. Document your communities thoroughly and consider using the second part of the community value to encode information. For example, 65001:1xxx could be for route types, 65001:2xxx for geographic regions, and 65001:3XXX for special actions. This systematic approach makes your configurations much more maintainable. AS path manipulation techniques. AS path manipulation goes beyond simple prepending. You can use regular expressions to match complex AS path patterns and implement sophisticated routing policies. This is particularly useful in networks with multiple upstream providers and complex peering relationships. Regular expressions in BGP use a specific syntax. The caret symbol matches the beginning of the AS path, the $ symbol matches the end, and the underscore symbol matches any delimiter. For example, caret $65,100 matches routes originated by AS 65100, while underscore 65100 underscore matches any routes that passed through AS 65100. In this slide's example, I am showing 3 common AS path matching scenarios. First, we match routes originated by a specific AS. This is useful for applying policies to all routes from a particular network. Second, we match routes that passed through a specific AS, which helps identify and handle transit routes. Third, we match direct customers using $, which matches an empty AS path. One advanced technique I have used in large networks is AS path filtering combined with communities. For example, you might tag all routes that pass through a particular Tier 1 provider, and then use those tags to implement failover policies. This approach is more maintainable than hardcoding AS numbers throughout your configuration. Multi-exit discriminator MED deep dive. Let's dive deeper into MED and explore its nuances. MED is unique among BGP attributes because it's only compared between routes from the same autonomous system. This characteristic makes it perfect for load balancing across multiple links to the same provider but also limits its effectiveness in multi-provider scenarios. One critical concept to understand is MED determinism. By default, many BGP implementations compare MEDs in the order routes were received, which can lead to non-deterministic behavior. Cisco's BGP deterministic MED command ensures that all routes from the same AS are grouped and compared together, providing consistent results. Always enable this in production networks. The BGP always compare MED command changes BGP's behavior to compare MED values even between routes from different autonomous systems. This can be useful in specific scenarios, but should be used cautiously, as it can lead to routing loops if not all routers in your AS have the same configuration. In this example, I am showing a scenario where you have 2 connections to the same ISP by setting different MED values for different prefixes. You can achieve granular inbound load balancing. Remember that MED is evaluated after AS path length, so if one path has additional AS hops, MED will not override that difference. Load balancing with BGP. Load balancing with BGP requires careful planning because BGP is designed to select a single best path. However, there are several techniques we can use to distribute traffic across multiple links. The approach you choose depends on whether you are load balancing outbound traffic, inbound traffic, or both. For outbound load balancing, the simplest approach is using BGP multipath. When enabled, BGP can install multiple equal cost paths in the routing table. These paths must be identical, differing only at the point where the BGP decision process would normally use the router ID as a tiebreaker. This includes having the same AS path length, MED, local preference, and origin. Per prefix load balancing gives you more granular control. You can split your address space and prefer different exit points for different prefixes. For example, you might send all traffic destined to European networks out one link and Asian networks out another. This approach works well when you have relatively stable traffic patterns. Inbound load balancing is trickier because you are influencing other people's routing decisions. The most common approach is to split your address space and advertise different prefixes or use different AS path lengths on different links. Some providers also support unequal cost load balancing using specialized communities. BGP traffic engineering in cloud environments. Traffic engineering in cloud environments presents unique challenges and opportunities. Cloud providers like AWS, Azure, and Google Cloud have their own BGP implementations and policies that you need to understand. Let me share some insights from implementing BGP in multi-cloud architectures. In AWS, you can establish BGP sessions with direct connect and advertise routes from your on-premises network. AWS supports standard BGP attributes like AS path and MED, but they also use BGP communities extensively. For example, you can use communities to control route propagation between AWS regions or to implement local preference within AWS's network. Azure ExpressRoute uses BGP differently. They support both private peering and Microsoft peering, each with its own BGP requirements. Azure also implements route filters that you configure through the Azure portal, which then translate to BGP prefix lists. Understanding how these filters interact with your BGP advertisements is crucial for proper traffic engineering. Google Cloud's Partner Interconnect supports MED for load balancing across multiple connections, and they honor AS path prepending for influencing inbound traffic. However, they have specific requirements for the prefixes you can advertise and implement strict prefix filtering. Always check the cloud provider's documentation for supported prefix lengths and any special requirements. Route reflectors and traffic engineering. In large networks, route reflectors are essential for scaling IBGP, but they can complicate traffic engineering. Route reflectors only advertise their best path to clients, which can lead to suboptimal routing if not designed carefully. Let me explain how to implement traffic engineering in route reflector environments. The key challenge is that route reflectors hide path diversity. If a route reflector has multiple paths to a destination, it only reflects its best path to clients. This means clients lose visibility into alternative paths. This loss of visibility can impact load balancing and failover scenarios. The solution is careful route reflector placement and potentially using multiple route reflector clusters. One advanced technique is using the ADDPATH capability, which allows route reflectors to advertise multiple paths for the same prefix. This restores path visibility to route reflector clients and enables them to make their own best path decisions. However, ADDPATH increases memory and CPU usage, so it should be enabled selectively. In the configuration example, I am showing how to set up route reflectors with proper cluster IDs and implement policies that preserve traffic engineering attributes. Notice how we use route maps on route reflector clients to ensure that local preference and communities are preserved and properly acted upon. Conditional advertisement. Conditional advertisement is a powerful but often overlooked BGP feature that allows you to advertise routes only when specific conditions are met. This is particularly useful for backup scenarios and implementing complex failover policies. Let me walk you through how this works and when to use it. The basic concept is that you monitor the presence or absence of certain routes in your BGP table, and based on that, you advertise or withdraw other routes. For example, you might only advertise a backup route when your primary route disappears, or advertise more specific routes when you lose connectivity to a primary site. In the configuration shown, we are implementing a common scenario, advertising a summary route only when more specific routes exist. The advertise map specifies what to advertise, and the non-exist map or exist map specifies the condition. This configuration continuously monitors the BGP table and updates advertisements accordingly. One real-world application I've implemented is using conditional advertisement for disaster recovery. When the primary data center loses all its upstream connectivity, the backup data center automatically starts advertising the primary's address space. This provides automatic failover without manual intervention, though you need to be careful about split brain scenarios. BGP graceful shutdown. BGP graceful shutdown is a critical procedure for maintenance windows that many engineers overlook. When you need to take a router or link out of service, simply shutting down BGP can cause traffic blackholing and packet loss. Let me show you how to implement graceful shutdown properly. The graceful_shutdown community is a well-known community defined in RFC 8326. When you tag routes with this community, receiving routers should lower the local preference to make these routes less preferred. This allows traffic to shift away from the router being shut down before you actually disable BGP. The process involves several steps. First, you advertise all your routes with the graceful shutdown community. Then, you wait for traffic to drain away. This typically takes 60 to 300 seconds, depending on your network. You can monitor interface counters to verify traffic has moved. Finally, you can safely shut down the BGP session or perform maintenance. In my experience, it's also important to coordinate with your NOC and upstream providers when performing graceful shutdowns. Some providers have specific procedures or communities they prefer you to use. Always test your graceful shutdown procedure in a lab environment first to ensure it works as expected. BGP security and route validation. Security is paramount in BGP traffic engineering. Without proper security measures, your traffic engineering policies can be undermined by route hijacks, leaks, or misconfigurations. Let me cover the essential security practices you should implement alongside your traffic engineering policies. Route validation using RPKI, Resource Public Key Infrastructure, is becoming increasingly important. RPKI allows you to cryptographically verify that the AS advertising a prefix is authorized to do so. When combined with traffic engineering, this ensures you are engineering traffic to legitimate destinations. Prefix filtering remains one of the most effective security measures. You should filter both inbound and outbound prefixes. Inbound filters protect you from accepting invalid routes, while outbound filters prevent you from becoming a transit AS accidentally. The example shows both maximum prefix limits and explicit prefix lists. AS path filtering is equally important. You should never accept routes containing your own AS number, unless you are specifically doing AS override, private AS numbers from eBGP peers, or impossibly long AS paths. I typically set a maximum AS path length of 10 to 15 for internet routes, as legitimate paths rarely exceed this length. Monitoring and troubleshooting. Effective traffic engineering requires continuous monitoring and the ability to troubleshoot issues quickly. Let me share the key commands and techniques I use for monitoring BGP traffic engineering policies and diagnosing problems when they arise. The Show IP BGP command is your primary troubleshooting tool. Adding various parameters provides different views into the BGP table. Pay particular attention to the path selection indicators. The greater than symbol shows the best path, the asterisk indicates a valid path, and the letter I denotes an IBGP learned route. Understanding these markers helps you quickly identify why BGP chose a particular path. When troubleshooting traffic engineering policies, I always check the BGP attributes in order of the path selection algorithm. Start with next hop reachability, then check weight and local preference, then AS path length, and so on. The Show IP BGP regexp command is particularly useful for finding routes matching specific AS path patterns. For monitoring, consider implementing BGP session logging and tracking prefix advertisements over time. Many network management systems can alert you when BGP paths change or when the number of prefixes received crosses thresholds. This proactive monitoring helps you catch issues before they impact production traffic. Real-world scenario. Multi-homed enterprise. Let me walk you through a real-world scenario I implemented for a multi-homed enterprise. This company had connections to 3 different ISPs and needed to implement sophisticated traffic engineering for both inbound and outbound traffic. The requirements included primary/backup configurations, geographic traffic steering, and automatic failover. The topology shows AS65001, the enterprise, connected to 3 ISPs. ISP1 is the primary provider with high bandwidth. ISP2 provides regional connectivity to Asia Pacific, and ISP3 is a backup connection. The challenge was to prefer ISP1 for most traffic, use ISP2 specifically for Asia Pacific destinations, and keep ISP3 as a pure backup. For outbound traffic, we used local preference to implement the policy. Routes learned from ISP1 got local preference 150, ISP2 routes got 100, and ISP3 routes got 50. However, we used AS path matching to identify Asia-Pacific routes via ISP2 and set their local preference to 200, making them preferred over ISP1. Inbound traffic engineering was more complex. We used AS path perpending on ISP3 to make it less preferred. For ISP2, we advertised only specific prefixes used by the Asia-Pacific region. We also worked with ISP1 to use MED values for load balancing across multiple connections to their network. Advanced community-based traffic engineering. Now, let's explore advanced community-based traffic engineering techniques used by large service providers. These techniques go beyond simple tagging and implement sophisticated, customer-controlled policies. Understanding these advanced patterns is crucial if you are working with major ISPs or building a service provider network. The configuration example shows a tiered community structure. Communities in the 65001:1XXX range control local preference within the provider's network. This allows customers to influence how their traffic enters the provider network when there are multiple entry points. Communities in the 65001:2XXX range control route propagation to different peer types. Action communities in the 65001:3XXX range trigger specific behaviors like blackholing or no export to certain regions. The blackhole community, 65001:3666, is particularly important for DDoS mitigation. When you tag a route with this community, the provider drops all traffic to that destination at their edge, protecting your infrastructure. Geographic communities in the range allow for fine-grained control over where routes are advertised. For example, you might want certain prefixes only advertised in Europe or only to specific peers. This level of control is essential for content delivery networks and global enterprises managing their traffic patterns. Automation and BGP traffic engineering. As networks grow in complexity, automating BGP traffic engineering becomes essential. Let me share approaches to automation that I've successfully implemented in production networks. Automation not only reduces configuration errors but also enables dynamic traffic engineering based on real-time conditions. The example shows a Python script using the BGP Python library to automatically adjust traffic engineering policies based on link utilization. This is a simple example, but it demonstrates the concept. The script monitors interface statistics and adjusts local preference values when utilization crosses thresholds. In more sophisticated implementations, you can integrate with your monitoring systems, IPAM, IP address management, and orchestration platforms. For example, you might automatically prepend AS paths when a link approaches capacity, or adjust MED values based on latency measurements. Configuration management tools like Ansible, Terraform, or vendor-specific tools are essential for maintaining consistency across your BGP configurations. These tools allow you to define your traffic engineering policies as code, version control them, and deploy changes safely. Always test automation scripts thoroughly in a lab environment and implement safeguards to prevent automation from causing outages. Best practices and common pitfalls. After years of implementing BGP traffic engineering in various environments, I have compiled a list of best practices and common pitfalls that every network engineer should know. Following these guidelines will help you avoid the mistakes that can lead to outages or suboptimal routing. First, always document your traffic engineering policies thoroughly. Be sure to include not just what you are doing, but also why you are doing it. Business requirements change, and without proper documentation, future engineers, including yourself, won't understand the reasoning behind complex policies. Be conservative with AS path prepending. I have seen networks prepend 10 or more times, which is excessive and can cause issues with some BGP implementations. Usually, prepending 2 to 3 times is sufficient. Also, remember that prepending affects all upstream providers, not just the immediate peer. Test your failover scenarios regularly. Many traffic engineering policies work perfectly during normal operations but fail during unusual conditions. Set up a lab environment that mirrors your production network and test various failure scenarios. Pay particular attention to how your policies behave during partial failures or when receiving unusual routes from peers. Summary and next steps. We've covered a comprehensive range of BGP traffic engineering topics in this presentation, from basic concepts to advanced implementation strategies. Let me summarize the key takeaways and suggest next steps for mastering BGP traffic engineering. Remember that BGP traffic engineering is as much an art as it is a science. While the technical mechanisms are well defined, choosing the right approach for your specific situation requires experience and judgment. Start with simple policies and gradually increase complexity as you gain confidence and understanding. For next steps, I recommend setting up a lab environment where you can practice these techniques safely. Use virtualization platforms like EVENG or GNS3 to create multi-AS topologies. Practice implementing each technique we've discussed, and observe how BGP makes routing decisions. Pay particular attention to how different attributes interact and override each other. Stay current with BGP developments by following IETF drafts and RFCs related to BGP. Join network engineering communities where you can discuss real-world scenarios with other professionals. Consider pursuing certifications like CCNP Enterprise or JNCIP that cover BGP in depth. Thank you for your attendance. Please consider subscribing to the channel.